speaker is Professor D Ramakrishnan from Caltech, and he's going to talk about relative trace formula, periods, and L values of U21 cross U11.
Hello, can you hear me? Okay, thank you. So, okay. I should start by saying it's a great pleasure to be here for Harish Chandra's centenary conference. So thank the organizers, Professors Raghunathan and Deependra Prasad for inviting me. It's been a great pleasure and enjoyed a lot of talks, and I'll probably enjoy more. And I only knew Professor Harish Chandra for 1 year, as I said yesterday in the afternoon, that really I had seen him before, but I only got to know him for 1 year, the last year of his life. But he was very encouraging. I should say that I told him that I was a student of Jacques, but I was also getting interested a lot in number theory, and I was trying to mix the two, and he was very encouraging actually about that, so I'm thankful to that. Okay, so today I'm going to talk about, I'll start simple because I was told to say something that might be good for students, and I will, so maybe I'll give so essentially, can you still hear me? Okay. All right, thank you. So there's so what I'm going to talk about really is about joint with work with Philippe Michel and Liang Yan, and we have a very long paper. I forget the title myself. Okay, maybe I'll keep it here. So I'm giving you this because if somebody wants to know details, you could always look at it. It's been posted on the archive just 3 weeks ago, I think, or at most a month. And it's called Bessel Periods on U21 with U11, and then relative trace formula and non-vanishing of L values. Okay, so it's a very long paper. It's like about 154 pages. There's no way I can actually it was over 200 pages which we compressed to make it somewhat reasonable. And then suddenly first part, the second part, maybe another 50 pages, not. But anyway, so there are two really completely distinct problems, and we addressed one of them about non-vanishing of L functions. So essentially I'm going to just try to explain some very simple basic things, and then if you want details, I'll be very happy if anybody reads this paper, even just a few pages, and make comments. I would appreciate it. Okay. All right. So one of the basic problems, in some sense, is that if you take an L function in the sense of Langlands, yeah. Yellow, oh, sorry. Okay. Can you see now? No? I thought all right, yeah. Okay. So essentially there's the Langlands L functions. I will just write it like this. So this is a Langlands L functions, and I won't explain what the terms are, and I will assume that it's analytic, perhaps with some pole at s equals 1, but nowhere else. And I will assume in the case where this is self-dual L function, so I will look at only L functions over Q. So even if you look at L functions over a quadratic field, we would induce it and consider it over Q. So I'm looking at self-dual L functions, and there is a thing called the root number. So then the root number of this, which is sometimes called W, it's plus or minus 1, because it's a self-dual case. And also this L function relates the same from S to 1 minus S. And the question is very often, so there are two questions arise, and both about the, I'm assuming it has analytic continuation. So the question is, what can you say about L1 half pi, or R, if you like? And the question is, if the root number is minus 1, of course it will always vanish. So let's assume that the root number is plus 1. Then you want to know when will they be non-vanishing for many pi? Is the question. And typically they vanish and not vanish. That's why it's very interesting. And for example, even for pi GL2 and associated to an elliptic curve, one knows that these questions are related to the Birdsman and Dyer and other conjectures. So it's very important to try to understand when this is 0 or not. And the other question is let's assume that this has an analytic continuation. It means no pole analytic in the S-plane. Then one wants to know if this is L1 half pi is greater than or equal to 0, which would be predicted by the Riemann hypothesis, but it's very difficult. So it's a very difficult question. So in fact, one knows. So anyway, so maybe I'll say here the second question is even open for even pi, which is so Ls pi r is Ls chi, where chi is a quadratic character. So it's a GL1 L function, and R is a standard representation. So even for this L function, we don't know whether this is greater than or equal to 0. And this is actually very typical in number theory, I think. A lot of questions about GL1 are very difficult, like things equal zeros and various things. And it's kind of like analogous to the situation in geometry, where the lower dimensional, like 3-dimensional case, is much harder than higher dimensions, because there is no room in some sense. So in fact, because it's for students, I want to say that if you take chi, the special cases, suppose chi is chi minus d, which is a quadratic Dirichlet character attached to a quadratic field, q squared. So minus d is the discriminant of this quadratic field. And in this case, if we know if 2 holds for all d, then you can prove that the class number of h, it's written h minus d usually, or hk if you like, is greater than, so d to the 1/4 minus epsilon. So this of course depends on epsilon. So this is a part of a Gauss's problem, and I will have nothing to say about it. This is purely for motivation. Because I just want to say it's very difficult. The best one knows using Gross-Zaghi and various people is bounded below by log D. That's all one knows. So in fact, Gauss conjectured there should be d to the 1/2 minus epsilon. So this implication is. So one expects in general, and also I should say 1 for the same quadratic character, L1/2 pi minus d is expected to be non-zero, and this is sometimes called Chowla's conjecture. Again, it's completely open. We don't know. So it's, anyway. Okay, so we've talked about a lot of hard problems, but let's talk about simpler ones. So, okay. And maybe I will, so one of the things that interests me is that these L values often also appear in relative trace formula. And so the idea is to try to see if you can use things like relative trace formula to say something about how often the L values vanish. I'm always interested in the center, which is the most important point for everything. Okay, so maybe I should say one more thing. It's a very important remark, is that Wolfsberger the L1/2 pi is 0, so actually more for even with twists, and for pi on GL2 over Q. And this was extended by Jacquet and with several people actually, Zagier and various people, ended with Go Jacquet. So it's a very nice thing that it's true that you can actually prove something for GL2 that you don't know is true or false for GL1. So it's not an unusual occurrence. Just like we can prove there are no Ziegel zeros for GL2, but we can't prove it for GL1. It's so. Okay, so maybe I will. So this was the kind of the 0th section. The first section I want to say something about relative trace formula. I will write RTF for this relative trace formula, and this is really of Jacquet, who was my advisor, and many years ago. Anyway, so I will say something very quickly. So again, I'm going to give a kind of an impressionistic lecture because it's just very long and complicated, the details. So I want to know that, but I will be trying to be precise about what I say. So the point is that you take, say, G to be some group, and then gamma is a subgroup, and I want this to be actually a discrete subgroup of G, which is a semi-simple Lie group. And then idyllic analog. But to have the idyllic analog, you have to look at discrete groups of congruence type. So if you want, I will assume congruence type. So idyllic analog. And anyway, when I write G like this, I would mean either G mod gamma or the idyllic version, G of A mod G of Q, where G is a semi-simple group. If you take with the adjoint group, I will restrict myself to things that come up in the adjoint group, G modulo center. So you can do more generally, but I won't. Okay. So of course now, so in the beginning at least, you can think of. So maybe as a first.
Can I ask a question?
Yeah.
Is there any sense in which the cases where you can regards self-dual, rectified,
Right. Yeah, so in the, so thank you, that's a good question. So when it's self-dual, it's either orthogonal or symplectic type. And in the orthogonal type, the root number is proved in many times is to be +1, many cases. So when things are +1, it's very hard to, always +1, that it's very hard to know it's non-zero. So it's the same problem we have for the symmetric square of the modular forms that Walsh-Bourget looked at, to know whether it is, So it's always the orthogonal ones are difficult. And symplectic ones where there is a flip, it's kind of somehow better. Yeah. So the ones that Walsh-Bourget considered, it can be 1 or -1. And his conditions, actually I should say precisely, when maybe that's why you're asking, W is +1. So when W is -1, sometimes you can twist it to make it +1, but yeah, so you want to look at the root number is +1. Okay, did I answer it? Is that okay? All right, thank you. All right, so as a first step, think of G mod gamma compact. Then of course this L2 G mod gamma, there are some representations in G hat of M pi gamma times, maybe I'll write V pi, and pi V pi are irreducible unitary representations, which is G hat. Representations, and these are finite multiplicities. So things are very nice, and you can do a lot of things. So if gamma is only, so even when gamma is not compact, but has finite volume, which is what we will assume. Again, I'm saying this for students, please, the experts, ignore this. You can take a nice nap for the first 10 minutes and then attend maybe. So finite volume, then we know that the L2 G mod gamma, what I would be interested in is that this thing here has a discrete part and a continuous part, which was analyzed very deeply in Langlands' book on Eisenstein series. And then the discrete part decomposes like this, and then inside it is contained what is called the cuspidal part. If you don't know what it is, just imagine J mod gamma as compact. Okay, I can go further. Okay, so, and of course, I'm saying some things that are very basic. So now if I would take a function which is in CC infinity of G, then, okay, first of all, the G acts here by right translation. I will denote by here, maybe I'll call it rho 0 for this action on cusp forms. So if you take F here, then of course you have, it also operates on this space, L2 G mod gamma in the compact case, and anyway, it acts, and in any case, but then it acts nicely on the cuspidal spectrum. So, so this action here, if you take, let's take phi in L2 cusp mod gamma, then rho F of phi, and so this actually, so if you want to evaluate it at some x, or I will write it formally, it's given by like a pairing between the kernel times phi. So this will be in G. So this is the kernel function. The kernel function is written this way, gamma and gamma of f of, so this sends x, y to x inverse gamma y. So this is the kernel function. And then it's well known, or maybe it should be well known, as the trace of rho f, which makes sense in the space of cusp forms. I should really write rho 0 to be precise. Then this, anyway, so this is given by the integral of the kernel function over the diagonal. The diagonal is really g embedded inside g cross g. Well, to be precise, I should put brackets everywhere. Okay, so one knows, so what did Jacquet do? He had a very lovely idea. It's very simple, but it's a lovely idea. Is this an eraser? Thank you. Yeah. I didn't pay attention today, sorry. Okay. All right, so what Jacquet did was, Jacquet's idea was consider, so integrate the kernel function over not the diagonal, but over some h1 cross h2, where h1, h2 are subgroups of G, Lie subgroups of G, and typically semi-simple groups as well. And then you integrate this kernel. So essentially, therefore, you look at this KF, you're integrating, so it's a double H2, but in fact, more than that, you can integrate this against, you can integrate it against some functions on, let's see, maybe C1, C2 on H1, H2. So that means that I'm going to integrate this against C1, and it's better to, so this is XY, X, and then I will take C2 bar Y. It's natural to define it this way, then you take dx dy. So what does all this have to do with L functions? I'll come to that very soon. So the beauty about the trace formula, and the relative trace formula is the same, then you can write it in the spectral side and in the geometric side. So, so on the spectral side, let me just write this here. When you expand this on the spectral side, what you get is you get the multiplicities. So let's say that you have some orthonormal, let's say orthogonal basis of, let's say L2 cusp. And I'm going to choose nice functions there for the basis, and then I take Mj, and then I have some multiplicities, and then I have here, I'm going to have over H1. So this F also is there, so you're going to get double, over the first integral will be rho of F. Again, I should put rho 0, I would ignore this for now, and then times a to j of x times this C1 of x dx times the integral over h2. There's no more rho f, you just get a to j bar of y C2 bar. So on the spectral side, you get something like this. Okay. Again, please stop me if there's something is not clear. I'm pretending I'm in the co-compact case. Yes, I'm sorry. But if you look at our paper, we do everything very carefully. I apologize. Yeah. So I'm going to pretend that we are in the co-compact case, and of course I will be not honest and apply it if I have time to non-compact co-compact case. Okay. So please, yeah. So that's why I'm saying I'm not even writing rho 0, etc. I'm being, yeah. Again, the time is limited. I will have to give a course on it. to do it more in detail. Okay. So the point is, so remember, so what happens that suppose if for example, like here, suppose you've got C2 is 1 or something, so then what you get here is that you get H2 here, you get A to G bar Y dy. So this is like being distinguished relative to J2, right? So this is non-zero if this representation say A to J belongs to is distinguished relative to. So actually it's a very natural thing. Maybe I'll even say, so we're only looking at spectral side, but let me, so a key example, because it's always, for me, I always have to look at some example. So suppose you take G to be PGL2, where Q, so I will just write 2, and then, so PGL2 R, say, which is a congruent subgroup. Then I'm going to take H1 and H2 to be both equal to just the torus, which is in the image of this one. This is a very simple thing. Then what happens is that in this case, spectral side becomes, if you look at this case, and then let's say also these functions C1 and C2, we'll write them as characters. So this chi1, chi2. Then what you get is you get the sum mj gamma, and then, okay, so now we take essentially L1 half. So the other thing I'm going to do is I'm going to choose my function. I have to choose my function. I'm going to choose this function to be, let's say, given by a matrix coefficient of discrete series of weight k. I take that. Then essentially what happens is then you get the sum over these over weight k cusp forms. And then here you get L1 half of these CJs these eta j's may belong to representation. So you have to make it precise, but let me say it this way, times here some lambda j of f. So f is kind of like a Heck operator, if you like, and then at infinity it's the matrix coefficient, then you get L1 half, and then you also get L1 half pi j bar chi 2. So therefore you see the L values show up in the relative trace formula immediately, and that's why I'm interested in the relative trace formula more than in, well, I'm not saying I'm not interested in the regular trace formula, but the trace is important, but when I see L values, I think I can maybe exploit it. Okay, and that's a good question. So in fact, you can make it at any value, but I'm going to take it at 1/2. Yeah. Huh? Well, okay. So I was going to remark that here. So what happens is that, okay, so this is some earlier work with Rogowski. Yeah. So what happens is that you have to actually, they don't actually converge. So you have to regularize it, and you have to put an S parameter, and then you take S equals 1/2, actually. So that's what you have to do. So it's kind of like, when you just write it, it's a bit like S equals 0, and they don't make sense. So you have to stick in, so there is a process of, so maybe I should say here, this is some regularization. involved. So actually, to understand this paper of mine with Michel and Liang, it may be good to read if anybody is interested, our old paper with my paper with Rogowski from 2005. It's a Borel volume. So this paper here is called Average Values of Modular L Series. Via the relative trace formula. And this was in the volume dedicated to Borel. So pure, and this is something that for math and applications, this is one of the volumes brought out by Yao, which he asked us for, and I think volume 1. And this is dedicated to Borel. So in this we give all the details of this regularization and all that. So formally, I'm just doing everything kind of formally. Formally what you get is the L values, but he's right, you have to regularize things. So actually what we do with Philippe and Liang, we try to do the same. So in this case, what we have is PGL2 and T. Instead, we try to do it for U21 relative to U11. And what happens is that it's just much harder. It kind of becomes exponentially harder. So somehow we managed to do it. Okay. And I should also say, what about the geometric side? So the main reason people look at trace formula is you have the spectral side and the geometric side. So when you compute something interesting 2 different ways, then it's very useful. Okay, the geometric side. So remember, so the kf xy is, the kernel function is f of x inverse y, gamma y. So when you integrate this in the relative trace formula case, more generally, not just GL2. So remember, we were looking at this. And then you have kf xy, whatever. y. If you now, we can do the geometric side. And so the kernel function, of course, this has the sum over gamma, and then you can exchange it. Then you get the sum over gamma in gamma up to some equivalence, I will say in a minute, of some group, I'm going to call it Z gamma. Then here I'm going to get H1 cross H2 divided by Z gamma. And then I get the same thing here. I get f of x inverse gamma y. So now, so you have C1 of x, C2 of y bar, dx dy. So it looks like this. So now where does Z gamma, where Z gamma is gamma 1, gamma 2, such that gamma 1, gamma 2 inverse is gamma. If you work with GL2, I would do it up to center, but I'm working with PGL2. So it's kind of like the usual trace formula. You will have orbital integrals, and this is kind of, and then you will have centralizers of elements, and this is kind of like that, except it's not. So a priori, H1 and H2 may be different, but they are both sitting inside G. Okay. Any questions? No? Okay. Why do we care about these things? I seem to have come far from my question about vanishing or non-vanishing and so on. And the reason is, So the reason is this. Okay, so now to do this, you have to look at, so essentially this is what we are doing is we are looking at the double cosets of gamma, the gamma, right? So you have a set of representatives for this. Yeah?
The gamma is not finite.
Yeah, it may not be finite, yeah. Yeah. Good. Now it's a measure. Yeah. It's mu. So, sorry. I should write. Yeah, I have a bad habit of writing this meaning the volume. I apologize. Yeah. Absolutely. Yeah. You take it. Huh? Bracket? Oh, I don't you see my brackets. For me, this would mean G mod gamma. Huh? Sorry? This is the volume. You're saying I should put gamma. Oh, where did you say? Oh, here. Inside it.
Volume, then is round bracket, then square bracket.
Yeah. Okay. Oh, no. No. Huh? Sorry? No. Is that okay? I think it's okay. No, I don't mean the adelic points. Yeah. Brackets. Oh. Yeah. Brackets. You quotient. Yeah, that's what I mean. Yeah. Okay. So the point is, let's look at this special case because one can carry out a lot in general, but I wanted to say in the special case that I consider with Rogowski, inside of this T, it's really important to understand this example. So now we can explicitly write down what this looks like. Suppose we take gamma to be so in this case what happens is that you get three kinds of the double coset. There's I and then W. W is this vial element. And then you get the two unipotent elements, maybe I'll call n plus and n minus, which is 1, 1, 0, 1, and then the other one is 1, 1, 1, 0, 1. And then you also have W of these guys. And then you have the regular elements, and they can be written as 1, 1, 1, x, where x is not 0 or 1. So these are the regular elements. So when you do this in the geometric side, there are really three types of terms. The identity term. So what you have inside is like an orbital integral. Identity term, unipotent term, and then the regular terms. So what happens is that, so the nice thing is the nice fact, which of course one has to prove. So nice fact is that the geometric side, in this case, so maybe I'll just write. So let's combine it. So you get some mj, and then you have the L functions. So, and then you have to, because we're taking, so I said something wrong because I said here orthogonal basis, I think, and that's the natural thing when you take new forms and things. They're not orthonormal, so actually you have to divide this by the lengths of A. You have to divide by this eta j square. So what you get here is that you get this divided by, it turns out it's L1 pi j add L function. That's what you get in the denominator. And this thing here is three terms in the geometric side. And the point is the first term is a bit complicated, but it turns out to be 0 if chi1 is not chi2. It's not 0 in general. You have to regularize it further to make sense of this. So I will just say, assume chi1 is not chi2. So that's from this term. And then from this unipotent term, you get 2 times, let's see, 2 times some constant, depending on, remember, I'm looking only at forms of weight k. And let's assume we're in some level n, and let's assume for simplicity it's prime. Then you get 2ck times L1 chi1 chi2 inverse. So this is from the unipotent term. And then the last term, it's almost impossible to compute exactly. And this thing here is big O of n to the minus k over 2 log n. This is what we found. And it's kind of, so I just wanted to say, when I talked to Jacques and a few other people, they were, they thought I was crazy to try to compute the geometric side. Because usually when people apply trace formula or relative trace formula to functor reality, there are usually 2 groups. And then you try not to compute either side's geometric side, but instead you choose suitable functions so they're equal, so you don't have to compute it. But here it's the opposite. We have only 1 group, and you have to compute it. And essentially, my idea was to show that these terms dominate the ones from the regular term. But the regular term, in fact, is an infinite series. So it's not an obvious that it's actually bounded by it. It's a lot of work. Each term you can bound very simply, but the whole thing is bounded by this. And then we found actually this is actually an old result. This is already due to Bill Duke in analytic number theory, and he uses different approach, different proof. So I think it is very interesting. By the way, you can use this to prove that the L value at the center is non-zero for lots of pi. You can prove. But of course, for a given pi, you can't prove it. So you can prove lots of non-vanishing results. In fact, you can prove that. So you can prove from this that there exists, for cusp forms of weight, say k and level n, you can prove that there exists n over log n cusp forms with L 1/2, let's say pi is non-zero. Actually, so you can prove things, but more is known now, actually. They even know that there is a positive proportion and all that. So it's not as powerful as one would like, but quite a bit of it is known. So anyway, when I was talking to Philippe Michel, he said, in higher degree L functions, very little is known. Maybe we can prove this non-vanishing for lots of forms on other groups. We worked it out for U21 cross U11 that I will mention now. What time do I finish? In 15 minutes? Something? 20 minutes. Okay, good. So all I can. So that was the beginning of this paper. But already I think it's good if people are interested to read this. But I should say that in the case when chi1 is chi2, not only do you have to regularize it, then both the identity term and the unipotent term are non-zero. And it is hard to tell if they might cancel or not. So it turns out, luckily, that this term here, the second term kind of looks like n over log n, and this term looks like n. So the identity term dominates, but by only a small logarithmic term. The power of n you get is the same. So it's rather subtle. So when you want to prove something, asymptotically, you want to prove that. So again, the idea is the asymptotically, this thing goes to 0 fast. So then you want to say that one of these dominates, but if they are the same size, then it's very difficult to know which one dominates. Okay. Let me go to. Sorry, I'm only giving you, as I said, an impressionistic view. It's okay. So now let's look at the case U21. So in the case, I'm interested in G is U21 and H U11, and I'm going to take this to be the H1 and H2 here. So essentially, this is going to be a unitary group. I'm going to look at group defined over Q. This I'm taking the real points, if you like. So defined by associated to a Hermitian form on some imaginary quadratic field, Q squared minus D, and I'm going to take, of course, a signature 2-1. You can write a lot of matrix representations, and in fact, we have to deal with two different ones, and we have to sometimes go between the two. But anyway, so the idea is that we want to do here, so we want to consider, so we want to take the, so what we want to do is want to average, so here we want to average over cusp forms pi of, so maybe I'll say here holomorphic discrete series type, and it's usually, it's given by two integers, k1 and k2. So the one we take is d minus 2kk. Again, depending on which matrix coefficient you take, we have to do everything very explicitly. So the whole thing, we get information only because we do things very explicitly. It's kind of what Jacques likes to call working class mathematics. So it's like, it's not anything, you think very abstractly, then you, okay, great, but you don't know. You don't know how big things change. So D is 2kk, and so this is k1, k2, but I'm looking at a specific one, but in principle it should work for any holomorphic discrete series. And then we're going to take for the, on H, we're going to take just U11, we take, so pi prime, cusp form pi prime of weight, again holomorphic of weight 2k. So actually when you restrict this as Dipendra knows, Gross-Prasad conjectures, and they know which ones restrict when you go to U11. So this is one of the things that restricts it. So you take these, and what we do is we do a very similar thing to this paper with Rogowski, but everything is much harder. In principle, it should work for U1 cross U1 minus 1, but the analytic difficulties are forbidding, quite difficult. So I don't know. Okay, so maybe we'll okay. So this is a pyramid. As I said, Philippe Michel, and myself, and Liang Yang. By the way, Liang Yang is also a student. Now he's at Princeton, but he's really good, excellent student. Sometime you could invite him. He's really great. And by the way, since we did that work with Rogowski, lots of people have worked on using relative trace formula to prove things like subconvexity or other things about L values, and like my own former student David Whitehouse and Brooke Fagan. And recently there is this amazing big work by Paul Nelson, but it's in the Archimedean part. They don't take, we take at infinity, the discrete series, it's not general type like what Paul has. Paul's work is more general type, and it's, anyway, it's quite different, but there are a lot of people who have done these things. Anyway, so what do we prove? We prove that if you take, Okay, so we prove that this, if you take pi, let me just say, and then I'll conclude. So you take sk nu. Another problem is that there may not be all new forms, there are old forms for level 1, and you have to work hard to get rid of it. It's complicated, so I won't say here. So then you get L value of 1/2 of pi e plus pi e prime. So let me explain what it is. Pi e is the base change, so really to be precise I should do it adelically. But pi is a form SU21 or U21, and then you base change to E, then U21 base change to E is GL3. Base change to E, then you get GL3. So this is the real. So same with U11 base change to, and I'm going to define both relative to the same quadratic field. And so these things are base change to GL3. So this is GL3 form, and this is on GL2 over E. So therefore this L function has degree 6 over Q, and therefore it has degree 12 over, degree 6 over E, so it has degree 12 over Q. So it's kind of not many results are there like this at this degree. So maybe I should say, in analytic number theory, they study a lot about the L values and non-vanishing. What they do is they also average, but then they average and they use the approximate functional equation. And when you use approximate functional equation, things get impossible with the degree of the L function. So after degree 4 or 5, it's like very difficult to prove anything in general. So our whole idea is to use the relative trace formula to get some information, maybe not as precise as one would like, but more general. So think here, and then this thing here, so this is from the spectral side. Well, really to be precise, I should also divide by 1/2 pi e adjoint L function, L1 pi prime e add. So here I'm going to fix pi prime, and then I'm going to choose its level n prime to be split in E. I'll tell you why in a minute. And then n here is going to be prime, which is inert in E. Again, why do we do that? That's a simple way, it turns out, to make sure that the root number is +1. Okay, so if the root, otherwise you have to always have some condition to make the root number 1. We can't be proving things about root number -1 because it's always 0. So L1 has a thing here. Then you've got 3 terms here, the same as before. You get the identity term, then the unipotent term, and then the regular terms. So, and a lot of the problem is to show that this thing here goes to 0 as n goes to infinity. This is very difficult. It's like doubly infinite, and so the difficulty, complexity increases with rank. This is the rank, even though it's rank 1 is a real group, Lie group, but as a complex Lie group, it's like GL3, so it's more complicated. So if you look here, what happens with the identity term, you get roughly k cubed n cubed, where k is this weight that comes up, and n is the level. And then here, the next one, luckily the unipotent term is like k cubed n to the 3 minus delta for some very small delta. It's not easy to prove. This is like a tremendously hard work. Whereas in this case, the unipotent part was very easy. You got something explicit, and then this is what you get, and then you also get L value of abelian L values. So, so this is what we proved. Therefore, the corollary is that, so for pi prime, so, and then for pi prime fixed, and then I should also say that our current result, we're assuming k is bigger than 32, but it's a technical problem. should work all the way from 2 onwards. I mean 1 onwards, because it's 2k. But we are, so therefore if I write in this normalization, I'm sorry, it should be 16. So for pi prime fixed, so what it says that and k fixed if you want. We can also vary k. Then we get pi e cross pi e prime is non-zero for, in fact, for infinitely many n. So everything is fixed, but you can make it, you can quantify it more. In fact, if this theorem 1, 2, we prove in fact that, in fact, this is, doesn't follow from theorem 1. It actually says that the number of pi of this type in this space of this type, okay, such that L 1/2 pi e cross pi e prime is non-zero. This you can, if you look at the thing here, this goes like it's greater than n to some alpha. Let me say this, for some alpha positive. So that means some positive power of alpha. It goes like n. It's not positive proportion, but so this is pretty hard because we use this technique called amplification to go from here to there. It's actually more difficult. Sorry, capital F? Where is capital F? N. Capital N is the level of pi. Pi n is a conductor. U21. Yeah. U21 conductor of pi, yeah. Yeah, that's right, yes. Yeah, no, actually, no. Well, actually, no, actually we take the, sorry, n is going to be square, did I say that? Oh, no, n I'm even taking prime. It actually works for square free. So if it's prime, I'm looking at things that are Iwahori fixed at n. So that should be the same as the conductor when you go to GL3. N is inert. Inert. N is inert in E. Yeah. So I have to see p squared. Right. It's not, what? That's in the rational. That's the norm of p. So I'm saying Iwahori level. So when I say n is p, right, prime, this is so this is a prime in E, right? And it is degree 2 over Q. So it's still prime level over E. Its norm is p squared. So I don't know what. Yeah. Conductor is an ideal in E. Yeah. I think we are saying the same thing, but yeah. Okay. All right. Yeah. Yeah, Iwahori level. Yeah. So we're trying to do this actually with supercuspidal, because if we do that, we will be able to prove some subconvexity in the level aspect. But we haven't done that yet. So it's Iwahori level. Yeah. Okay. What did I want to say? Oh, maybe the last thing I would say. I have 2 minutes, right? 2 minutes? Yeah. Okay. All right. Okay. So I just wanted to say that maybe 2 things very quickly. So in our thing, what we get the period. So if you take phi and phi prime, this is in pi and this is in pi prime. So what we get is the information about the sum of this divided by phi times phi prime. So each individual one here, then this is related to, so this is by GGP and Gaon Rose Prasad and also Ichino Ikeda formula. And so you have this thing was known when we started to, well, some factors that are understandable and positive bad factors times the L function and so this was proved by like Bazar-Plessis and Wei Zhang and Xinmin Zhu and so we use their results because what we have is this, but one thing we could check also is that these local factors also we proved to be positive. So, and then this is positive from the construction, so therefore that's why we are able to then conclude that the L function is also positive. So it's really using their things plus some local computations. It's not obvious to us that the local things are positive. Took a while. Okay. And the other thing I wanted to say is that the Bloch-Kato conjectures say that when this function is non-zero, this thing here implies that certain Selmer group associated with some Galois representations you attach to this, then this is has rank 0, L rank 0. And this actually is also known, well, essentially known, I should say, and this Harish's conference, I should say, it's probably not right to say, but probably known by various works of Wei Zhang and Xinmin Zhu and so on. They told me they did it for forms on U3 which give rise to cohomological forms with trivial coefficients, but some of their students are doing it for non-trivial coefficients. So assuming that, so therefore you can ask, why do we care? Oh, no, that's not it. Sorry, the L function is non-zero, implies the Selmer group is finite. And so it's kind of interesting. It's very much like the points of an abelian in elliptic curve. So it's interesting to know that these are non-zero. Anyway, that's all. Sorry.
Any questions?
Yes, please.
When you call the rest of the terms regular, are they really regular or could they be
regular and semi-regular?
Semi-regular.
Yes.
And those also go to 0.
Yeah, they go to 0. That's yeah. So it breaks up into several parts, and yeah, exactly. Yeah, it's for GL2. It's a good exercise. It's actually nice to read. It's only 4 or 5 pages, and here it's like 50 pages. So, yeah, sorry.
Can I also make another positive? The local Chino-Ikeda periods. This has been proven in general.
Yeah. For UN cross UN plus 1, it's proven.
No. For all cases, the positivity of the local periods is known.
You mean the bad periods? Oh, okay. Yeah, I didn't know. Yeah, we proved it in this case, but yeah. No, I'm not surprised. So anyway, I'm giving these as a reason why you might be interested in these results. Yeah, that's all. So yeah, we actually have nothing to do with proving that. Yeah.
So in the first theorem, there's a k cubed, k to the 3.
Yeah.
And do I understand correctly that this weight aspect is lost in the amplification?
Sorry, I can't.
In theorem 2,
yeah,
there's no K in the lower bound anymore, so this is lost in this amplification that you mentioned?
Yeah, so I'm saying if you fix, it is, but the point is that I'm saying if you fix K here, fixing pi prime and K, yeah, so there is a same K is also there. You can also vary K, but I'm saying if you fix K, then it doesn't matter. So this is it's included here, K and N prime. But if you want, you can make it clear what K is. It's also K cubed. Yeah, it's the same K. Yeah. Yeah. If you don't also vary K, then you'll have to put K cubed in here. Yeah. The two weights are, in our case, it's minus 2K comma K. And then the U11 also weight 2K. So in fact for U11 for these things, the weights go from K to 2K. They all appear. So we took this one because we could write an explicit matrix coefficient for the U21 discrete series, which when you restrict to U11 gives you a matrix coefficient for this representation. It's not easy to find such a thing in general. It is holomorphic discrete series. Yeah. Huh? Yeah. Yeah, some other, yes. But what happens is that it doesn't restrict exactly to the matrix coefficient, but you know, it can be written as a sum and then you can separate it. But we don't have a nice form. This is like very nice that when you restrict, I don't know if it's how common it is. You have a bigger Lie group and you take the matrix coefficient of a discrete series, restrict to the smaller group. In general, it'll be a sum of matrix coefficients of some finite number of, but here it turns out to be exactly equal to 1. We were really surprised. So it's, yeah. I don't know how often that happens in general for G and H, I don't know. It's just yeah, holomorphic to holomorphic. But if you take our discrete series, the restriction will have all the holomorphic discrete series of weight from K to 2K. All of them will appear from K to 2K. Maybe with parity, yeah. But no, yeah.
For theorem 2, you will need to know, I suppose, that the individual L values are not too large. So
yeah.
Do you use subcomplexity?
No, we don't. We prove something that is not yet, not subconvexity, but we prove some bounds. That we have upper bounds and lower bounds for the L value.
Convexity is not enough either, is it?
For subconvexity, it's not enough.
But for this, you need convexity enough?
No. Actually, to get some power of n, we just need some bound close to which we call quasi-convexity. That bound is enough.
So a little stronger than the shear convexity.
It's not stronger. So the point is, see, the thing is, there is conductor dropping here because the terms involve n cubed. So the dimension, so the formal degree, when you compute it, you get n cubed here, but that's not what you get from.
No, but my point is,
yeah.
The left-hand side in your term 2, if there is one representation such that the L value is very large,
yeah,
then you cannot say anything.
Right. Yeah, we do have upper bounds for L values, but I'm saying because of conductor dropping, we don't get we don't get convexity. If we got convexity, then by amplification we can get subconvexity. Okay. But the conductor dropping case is difficult because you have the formal degree, if you like, comes up in the Weil law, but then that should be 1/4 of the conductor, but it's not going to be. So whereas in the generic case they're equal, so then you get convexity and you can break that's what happens that's why we are working right now with supercuspidals, because then the generic supercuspidal, you will get equality, you'll get convexity, and then we can break convexity. But nevertheless, we still use amplification here for this to get better bounds. So it's important. Yeah, I agree. Without getting a better bound, you can't prove it. It's a very hard theorem. Yeah. Sorry. I don't. Yeah. Right. Thank you. Yeah.
Thank you. you. So let's thank the speaker again.
Okay.